And that's my next slide, which I called again spectral analysis of projection maps, number 2. So here's my projection picture. Again, I have my two vectors like this. I do this because actually it's a beautiful piece of the argument. I mean, those two observations we just did on my slide before, on the example, on the three-dimensional example, I'd like to establish these observations now in a formal way, in a general case, and I do this just because it's a nice result to remember, but I do it also for the reason because it's a beautiful proof, it's a beautiful usage of that machinery we have built together so far. It's a beautiful proof. Look at this. So here's my projection map. Again, it's this repetition of what was on the other slide, which takes n-dimensional vectors into n-dimensional vectors. Here's my formula for the projection map. It's a dot product of A and B by the length of B squared times B. Like I said, projection map only makes sense when the vector B is non-zero, otherwise it doesn't make sense. I also said earlier that it's only it will be non-trivial when dimension is 2 and larger. For the dimension 1, projection map doesn't make much, it does make sense, but it doesn't bring anything non-trivial. It will be just identity map. Here's the lemma, which states what we discovered with you earlier. Part A says T has two eigenvalues. All the time, no matter what the B vector is, no matter how large the dimension is. One of them is 1 and the other one is 0. Part B says that the eigensubspace associated with the value 1 is always just a span of the B vector, which is at the base of my projection. And part C says that vector B is perpendicular to the eigensubspace of the 0 value. And that's the explanation of what I mean by this writing. It's a subspace, and that's the vector. So vector perpendicular to a subspace, when vector perpendicular to every element of that subspace. It's a free observations we made on the example from the slide before. I'd like to establish these observations formally now. Look how beautiful the proof is. I'll start with the assumption that we have a vector, and I'll start with the assumption that I have eigenvalue and eigenvector of a projection map. So the assumption will be as general as this. Imagine I have a value, a real number, and a vector from Rn. Vector is non-zero, and it is the eigenvector and eigenvalue. So here's my relation, which connects eigenvector and eigenvalue. I don't make any assumptions about what the lambda is. I'm not making any assumptions what the x is. Just any arbitrarily chosen eigenvalue and eigenvector. Okay, if I use this vector, if I use this formula for the projection map, then this identity becomes like this. If I just replace left-hand side with the formula from here, that's how it will be. X dot product with B divided by the length of B squared times B, it's the left-hand side. Right-hand side, I'm not changing it. I'm just keeping it as it is. All I did, I just substituted the formula for the projection map. Now I'd like to take everything on the left-hand side. I'd like to take this right-hand side on the left-hand side. So this is equivalent to, I'm just taking the right-hand side to the left-hand side. Look at this. Here's this coefficient. I put this in brackets just to emphasize that this is just a one single numerical coefficient times the B vector, take lambda times the X vector equals 0 vector. So far so good. It's just some arithmetic manipulations with the expressions. But now starts the actual analysis. When you look at the expression like this, what comes to your mind? When I look at the expression like this, what do you think should come to my mind? Is that the linear combination of two vectors? Oh yeah, of course, linear combination. Yes, it is a linear combination of two vectors, and we discuss linear combination in the context of what? Of two things, linear dependence and linear independence. That's what I'm going to do now. I'm going to consider two possibilities, 1 and 2. Well, if you're not sarcastic, then I'm with you. We're going to consider two possibilities. The pair of vectors B and X linearly independent. That's one possibility for two vectors to be. And the other possibilities, these two vectors are linearly dependent. Let's just see what happens. Let's just analyze these two possibilities. If they are linearly independent, then we all know linear combination of such vectors equals 0 only in one case, when both coefficients are 0. So if they are linearly independent, then we can conclude straight away that both coefficients here, lambda and this huge bracket, they must be 0. Lambda is 0. For the bracket, I'm going to take only the numerator, because denominator is non-zero. Remember, vector is non-zero. Here we go. But dot product of x and b being 0, this is equivalent to x being perpendicular to b. And we just established half of the lemma, isn't it? We assume that lambda and x are eigenvalues and eigenvectors. With extra assumption that x and b are linearly independent, we concluded that the only possibility for the eigenvalue to be is 0, and the eigenvector must be perpendicular to b vector. It's both this case is established and this case is established in one go. Just with this one extra assumption that the vectors are linearly independent. Let's just see what happens if vectors are linearly dependent. Oh, as a matter of fact, well, I should add one extra argument here. Assuming that they are linearly independent, that just implies this. But you also have to claim the opposite way, that every time you have lambda 0, and every time you have a vector which is perpendicular to b, that will be an eigenvector, and it comes from here. If you have a vector which is perpendicular, that will imply by the formula of the projection, that would imply that t of x is 0 vector. And that means that every such vector is the eigenvector with the value 0. So in fact, this implication is reversible. And that will finish the analysis of the first possibility, b and x linearly independent. Now the second possibility, b and x linearly dependent, let's just see what happens in that case. Well, for two vectors to be linearly dependent, it means one is a scalar multiple of the other. It may vary which one is a scalar multiple of the other, but given that both of my vectors are non-zero, or given that b is non-zero vector, I can say that there is a number such that x is a scalar multiple of b. That's the interpretation of two vectors being linearly dependent. Why not I just use this formula now when I compute my t of x? Let's just do that. So if my x is mu b, well, by the way, actually, that's my what I would like to say is this, actually. We assume that they are linearly dependent. Two vectors are linearly dependent when one is a scalar multiple of the other. Just this alone already justifies this, you see? Every vector x like this will be in the span of b. All I have to see now is that the lambda in this case will be 1, and that's how I see it. Look at this. If my x is a multiple of b, then from here, if again I use the formula for t of x, this formula, if I sub in here if I sub in here mu times b, it's my substitution. In the dot product, this coefficient can be taken out. Here it is. And the dot product of b with itself, it's the length of b squared. So that will just take this, that will make this fraction just 1. And the whole thing just mu times b, which is x. And that's my relation between t of x and lambda x, with lambda being exactly 1. So x in E1. And that finishes the second part. The second possibility for the eigenvalue is 1, and this one is always true. You can't deny it's a beautiful proof.